I welcome you all to this supplementary session. In this session, we are going to discuss about a constant mesh gearbox, that is this gearbox. This gearbox is being used in Ashok Leyland 16-ton heavy commercial trucks. This has 5 forward speed and 1 reverse gear. Before starting the dismantling, let me just briefly introduce the components here. This is the input shaft where it receives power from the clutch. In these lines, the clutch friction disc will be get seated. As you see, as the gearbox is in neutral condition, this is the output flange. The output flange is not rotating now. Though I rotate the input shaft, as the gear is in neutral condition, the output flange to the final drive is not being rotated. And typically the driver operates this clutch lever. As the driver operates the clutch, as you see, this is a withdrawal bearing of the clutch. This has a bearing. As the driver presses the clutch, this lever actuates this bearing in this axis and disengages the clutch. In this way, the clutch is being disengaged. This is the gear selection rod. It receives the input from the driver. As the driver shakes the selector rod, it responds to that. And this is the output flange of this gearbox. This gearbox has already been opened partially and all the fasteners have been loosened in order to save some time. Also, all the bearing fittings have been machined so that the bearing is easily installed and dismantled, so that it will save us time. First, let me remove the gear selector rod tower assembly. So, this has secured by 4 bolts. Just I remove this bolt and this is where the gear selection happens. Then I am going to remove the clutch activation assembly, that is withdrawal bearing assembly. Now this is the input shaft. As we discussed, you can see the input shaft is freely rotating. Now these are the selector rods where the selecting rod knob will be sitting here and responds to the driver's reaction. Now I am going to open the top cover of the gearbox. So this is the inspection cover. So these are the 3 selector rods. So this selector rod is responsible of changing gears for reverse and first. This selector rod is responsible of changing second and third. This selector rod is changing the gears of 4 and 5. Okay, now I am going to remove the selector rod assembly. So these are the selecting rods, and on the selecting rods you would find the selecting forks. So this forks typically sits on this collar where it's used to shift the gears. So in this case we have 3 different collars. For this collar is responsible of changing first and reverse, and this collar is responsible of changing second and third, and this collar is responsible of changing 4 and 5. Now I am going to open from the rear end of the gearbox. I just loosen the flange nut that secures the drive flange. So this is a drive flange, and this is the main shaft of the gearbox. You can see now I am just rotating the input shaft, but there is no reaction from the main shaft as the gearbox is in neutral condition. Now I engage the first gear. You can see that now the output flange is started rotating along with the input shaft. As I bring the collar to the neutral, now again the flange gets stopped. Now if I suppose I get engage the reverse gear, then one would appreciate the direction of the rotation of the output flange of the gearbox. So this is the oil seal that prevents the oil leakage from the rear end through the flanges. Okay. This is a skew gear arrangement for the speedometer. This, as the output shaft rotates, it rotates along with the output shaft and gives the measurement of the vehicle speed. Now I open the input shaft cover. As you can see, the input shaft is supported through a deep groove ball bearing. I just simply remove the input shaft. In a real gearbox, this won't come out this much easily. We have to use the pullers to get the input shaft out. You can see also there is a cavity in the input shaft. This cavity helps to support the main shaft through the bearing. So the main shaft is supported at two ends. One is at the back end through a bigger ball bearing, at the front end in the spike rod bearing. It is kept inside the input shaft. Now I dismantle the main shaft step by step. First I loosen the main shaft lock nut. So this is the nut that secures the entire gear system into the position. Then I remove the bearing. Again I recall this bearing in usual gearbox, it won't come out this much easily. So this is the fixer dog and the sliding dog assembly. As this is the constant mesh gearbox, you would not find the synchronizer unit. Instead, you would find these two dogs. One is this known as fixer dog and this one is known as sliding dog. As you see, the fixer dog has splines here. So it is fitted splined on the main shaft. As whenever the main shaft rotates, the fixer dog rotates along with the main shaft, and this is how it rotates. And this is main shaft, fourth gear. As you see, the shaft gear is supported through a bush bearing. Inside there is no splines like a fixed dog. Okay, what it means is, through these splines, whenever the shaft rotates, the fixed dog rotates along with the shaft, but the gears doesn't rotate along with the shaft because the gears are supported through a bush bearing on top of the shaft. And this is a thrust washer. Just I remove the entire main shaft. So this is the main shaft. As you see, it has got splines. So it is main shaft third gear with the bush. And this is fixed dog and sliding dog assembly to shift second and third gear. And this is main shaft second gear. This constitute a set. As you can see, the main shaft gear has a clutching teeth here. It used to engage the sliding dog, and so this constitutes a set. Okay, so as in a real assembly, it will be looking like this. So as the main shaft rotates, the gears are independent to rotate freely without any problem. So once again I repeat. So the main shaft gear has no splines inside. It is free to rotate on top of the main shaft. But in between there is a dog that rotates along with the main shaft. If I connect this fixed dog and this clutching teeth of the gear through a sliding dog, then it became a single unit. This is how the gear engagement taking place in a constant mesh gearbox. So suppose if I want to engage the third gear, I just simply move the sliding dog upper direction. If I want to move second gear, I just go. You can see now the top gear is free to rotate, but sliding dog, fixed dog and the gear became a unit now. So this is a thrust washer once again. Now I remove main shaft reverse gear. Like all the gears, main shaft reverse gear also has the bearing, but instead of bush bearing, they have given needle bearing. Then the dog assembly. Then this is the main shaft first gear. With this, the dismantling of the main shaft is over. Now we are going to dismantle the reverse idler gear and the counter shaft. To remove the reverse idler gear, we need to lose this lock collar. Now I remove the reverse gear idler shaft. Then I take out the distance piece and the reverse idler gear. So this is the counter shaft assembly. So this is fifth counter shaft gear, fourth, third, second and first. But this gear acts counter shaft gear for the first gear as well as for the reverse gear. And the idler will be sitting like this. So whenever the counter shaft rotates, the idler gear also rotates along with the counter shaft. It means, what it means is, in a neutral condition, the clutch is engaged, the input shaft, the drive is received through a clutch disc to input shaft. So as whenever the clutch disc rotates, it rotates the input shaft. So it rotates all the counter shaft gears as well as the reverse idler gear and all the main shaft gears, because all the main shaft gears are floating on top of the bush. So it rotates. So whenever the engine start and the clutch is not clutch is engaged, then all the gearbox, all the gears in the gearbox will start to rotate, not the main shaft. Now I just open the front end of the counter shaft. So this is a counter shaft lock nut. I'll just also remove the bearings. Counter shaft fifth gear, distance piece, counter shaft fourth gear. As you see, unlike main shaft gears, it has splines. So whenever the counter gear rotates, the shaft rotates along with the gear. For the comparison, I just show the main shaft gear. So the main shaft gear, it is spline inside, there is no splines. So it's a major difference of main shaft gear and the counter shaft gear. Counter shaft third gear, and this is counter shaft second gear, and this is counter shaft first gear and the counter shaft reverse gear. So this single gear acts a counter shaft gear for both first and reverse. This is PTO cover, power takeoff unit. In some trucks, in some goods vehicle, you would find the tipper as arrangement where it unloads the material through hydraulic cylinders. The hydraulic cylinders, the hydraulic pump will get the drive from the engine counter shaft. So in the neutral condition, whenever the engine rotates, the counter shaft, we know that the counter shaft is keep rotating. From the counter shaft, we will get the drive to run the hydraulic pump. So in if there is no power takeoff unit, this is simply get covered with the plate. So with this, the dismantling of a gearbox is completed. Now before going into further discussion, we discuss why gearbox is necessary in a IC engine truck. For that, we will see some slides here. Why a gearbox is necessary for a vehicle, particularly a IC engine mounted vehicle. Any prime mover, it is expected to give a constant power throughout the range of the vehicle speed, that is like this. So this is vehicle longitudinal speed and the power characteristics and the torque characteristics. This is what we expecting from a ideal prime mover. We can realize this drawing as the power is being constant, the torque is coming down as the power is torque times omega. As the torque is as the power is constant, as the speed is also increasing, the torque obviously needs to come down. This is called ideal traction hyperbola. This is the curve we are looking forward in any given prime mover in any vehicle. But what is happening in IC engine is, if you see a typical IC engine torque profile, this is speed on the x-axis. On the y-axis, there are two curves. One is torque on the torque on the blue and power on the red. As you see, the IC engine, there are three demarcation I wish to explain here. First, as you see here, there is no torque or power on the near zero speeds of the IC engine. This is one critical point about the IC engine. And as you see there, the IC engine is capable of giving the peak torque at a particular range. not at the entire range, working range of the engine. Also the power keep increasing, and at one point it gives the best power for a given IC engine. So these 3 points are critical characteristics of a IC engine. First we will discuss this particular gap in a torque and power demands a clutch move of element. Without clutch, as you see, there is no torque and no power in this region. Because of this, a clutch become necessary to move the vehicle. The clutch is also called a move of element that uses to move the vehicle in a near zero speeds. Then here, as the engine speed increases, as you see the engine torque increasing, but at one point the engine torque is getting dropped. This is because the reduction in volumetric efficiency. As the engine speed increases, the volumetric efficiency also increases. At one point the engine does not able to maintain the volumetric efficiency. The result of that, the engine torque is keep coming down. Parallelly, one can see though the engine torque is coming down, the power is keep increasing. It is because of the engine speed is increasing, the power, because the power is torque times omega. Though the torque is coming down, still the omega is keeping up, so the power is able to going up. Still at one point the drop in volumetric efficiency is such that the drop in torque, even though the engine speed is increasing, the drop in torque is causing the power to coming down. This is omega max. This is where the engine gives the maximum power for the particular engine. Because of this characteristics, where the power and torque hits at a particular region for an engine speed or the entire range, the torque demand is required by the vehicle cannot be fulfilled by this characteristics. That is where the gearbox comes into picture. As a comparison is the ideal traction hyperbola, and this is the average or the typical engine torque characteristic curve. As you see, the engine torque is meeting ideal traction hyperbola at a small region. These are the mismatches. This is where the gearbox comes into picture. So what do we do here is, we try to scale up the engine torque with some factors. Suppose for example, if this particular gearbox has the ratio of 7:1 for the first gear. So we assume this is an engine torque curve. What we are trying to do is, we magnify the engine torque into 7 times. So the torque curve shifts here. At the same time, as the torque is increasing, the engine speed also reduces. So it is 7 times 1/7 the speed of the engine is reduced here. So the curve is shrunk and lifted to the top. So this is managed by the first gear, and subsequently the second gear, third gear and fourth gear, even though you can see some mismatches. So these regions are not met by the gearbox. So as you increase the number of gears, the gap between the expectation and the reality is keep reducing, and the vehicle found to be moving very smoothly. So this is the reason for the gearbox in a ICE engine fitted vehicle. In case of electric motor, at the initial region, the electric motor are capable to give some constant torque, and then it reduces the torque. Similarly, the power shoots up and maintain the power after the base speed. Now we see the schematic of this particular gearbox. So this is the input shaft, these are splines. So this is the input shaft. Where the clutch disc, friction disc sits here. As the clutch disc rotates, the input shaft rotates. That is this gear, blue one. So the blue one is permanently attached with the counter shaft gears. So whenever the input shaft rotates, all the counter shaft gears are rotating along with the input shaft gear. Also, the red ones are the main shaft gears. As you have already seen, the clutch, the input shaft makes the counter shaft gears rotate. The counter shaft gears makes the main shaft gear rotates, but not the main shaft. It is a very important point. As the gears are mounted on top of the bearing. So, whenever though the gears are rotating, the main shaft, unless you shift the gears, the main shaft will not rotate along with the gears. So, as you see, there are 3 selector rods, yellow ones. So, as the driver shifts the gears, there are cavities. You can see here. So, as the driver moves the lever, gear lever, he just the driver moves this rod. This rod moves on the cavities of the selector rods. So, here this selector rod is responsible of shifting first and reverse gear, and this selector rod responsible of shifting second and third, and this is responsible of shifting 4 and 5. As you see, these are the 3 forks what we already saw. These are 3 forks, and 1, 2, 3, 1, 2, 3. So, if the rod moves this way, the fork moves this way and it engages the reverse gear. If the fork moves this way, it engages the first gear. Then similarly, this is main shaft second gear, main shaft third gear, main shaft 4, main shaft 5. In main shaft fifth gear position, we simply mechanically connect the input shaft and the main shaft, the red one, through mechanical connection. There is no any gear reduction. It is 1:1. So, for gear ratio calculation, I just mentioned some alphabets to the particular gears: A, B, C, D, E. A, B, C, D, E, F are all main shaft gears. G, H, I, J, K, L are counter shaft gears. M is a reverse idler gear. We will see how to calculate the particular gear ratios for this particular gearbox. For the clarity, I have removed all the gears from the previous slides. So, in this slide, I have removed all the gears to emphasize how the first gear array is really working. So, it is a riveted gear train. A riveted gear is the input shaft and the output shaft are kept at a single axis. So, the input this is received to the gearbox through gear A, and it operates gear G. So, it is one gear drive. Typically it's under drive because input shaft is it's a smaller gear, and the counter shaft first gear is this is the counter shaft fifth gear, and this is the input shaft. This also acts as the main shaft fifth gear. So, as you see, it's under drive because this is the input shaft and this is the counter shaft gear. So, there is under drive. The gear ratio for this is number of teeth present in gear G divided by number of teeth present in gear A. This gives the gear ratio for this particular 2 gears, and the drive is transmitted to gear K. The speed of the gear G and speed of the gear K are same as it is connected in a single shaft. So, whatever the reduction happened here, the same ratio is being transmitted to the gear K, and it is driving the bigger gear here, drive gear E. Now, the ratio for this is the number of teeth present in gear E and number of teeth present in gear K. If we multiply both of these gear ratio, one would end up with the gear ratio of the first gear. This is how we are calculating the gearbox first gear ratio. For this particular gear, as you see, gear A contains 20 teeth and gear G contains 44, and gear E contains 51, gear K contains 16. If you calculate like this, you would end up in 7:1, meaning the input shaft has to rotate 7 times in order to drive the output shaft once. So, this is the first gear ratio. Likewise, one has to do all the calculations for all the gears. This is the final gear ratio. As in the fifth gear, the output shaft, the main shaft and the input shaft are mechanically connected. So, the gear ratio is nothing but a 1:1. Similarly, here for reverse gear ratio, it is 6.6:1, meaning the input shaft rotates 6.6 times, then the output shaft runs in a reverse direction once. This is how the gearbox gear ratios are calculated. Now, I am going to assemble the main shaft. So, this is main shaft first gear with the bearing. As you see, there is no physical connection between the shaft and gear and the dog assembly. As you see, the shaft is now, the gear is now freely rotating. As I engage the gear, now the gear is rotating along with the shaft. Now I put the reverse gear, main shaft reverse gear. This clutching teeth has to meet the fixed dogs. Now the thrust washer. Now the main shaft second gear. Then the dog assembly. Main shaft third gear. Again thrust washer. The thrust washer is installed at the end of the every set. This is called one set and this is the another set. Now this is main shaft fourth gear and the dog assembly. And this is the main shaft assembly, okay, with the drive flange. Now I fit the input shaft. So this is the drive line. So this is a counter shaft. This is counter shaft first gear and reverse gear, counter shaft second gear, counter shaft third gear. As you see, this is how the gears are stacked or arranged inside the gearbox. In the main shaft, you would notice the gear diameter is keep increasing, or at the counter shaft, the gear diameter is keep reducing. So this is input shaft, also acts a fifth gear of the main shaft. This is counter shaft fifth gear, fourth gear, third gear, second gear. As you see, there is no connection between the counter shaft reverse gear and the main shaft reverse gear. This is where the reverse idler comes into picture. So once again I repeat. So the engine is rotating at the clockwise. So whenever the two external gears are meshing, the gear is rotating at the opposite direction. So the entire counter shaft is rotating at the counterclockwise direction, and all the main shaft gears are rotating once again in the clockwise direction. But the reverse idler, through the reverse idler gear, it's changing the gearbox direction in the reverse gear. First, let us start with the assembling of counter shaft. Counter shaft, fifth gear. Put the thrust washer, bearing inner race, and the bearing. Now I put the counter shaft lock nut. With this, the counter shaft assembling is over. Now we are going to assemble the reverse idler gear. Now I put the collar, lock collar for the reverse idler shaft as well as for the bearing. I now going to install the needle bearing of the first gear, main shaft first gear, bush, and with the main shaft first gear. As a set, I put on top of the counter shaft gear. Then I insert. This main shaft assembling can be done in multiple ways. I now do it in my own way. Then the dog assembly for the first and reverse. Then main shaft, reverse gear, the clutching teeth should face the first gear. After the end of the first set, I put the thrust washer and I take second gear, main shaft second gear. After that, I take the dog assembly for second and third. Main shaft third gear. The clutching teeth has to face the second gear. Then the thrust washer, main shaft fourth gear. Dog assembly for 4 and 5. Now bearing that supports the main shaft at the input shaft end. Then I secure the entire main shaft assembly with the lock nut. With this, the main shaft assembling is over. I put the collar. Then distance piece, skew gear for speedometer purpose. Now the rear casing. On the rear casing, you can find a pinion that meshing with the speedometer skew gear. Then this gear transmission, the drive of the gear will be transmitted through cable to the speedometer to read the vehicle longitudinal speed. I put the flange lock nut. With this, the back end of the gearbox assembling is over. Now I come into front. I just inserting the gearbox input shaft. At the neutral condition, the input shaft is turning. As you see, the main output shaft flange is not rotating along with the input shaft. Now I am going to mark on the input shaft as well as at the output shaft. So both the marks currently at the top, I engage the first gear. So as per the discussion, I have to rotate the input shaft so as to get the one complete revolution of the output flange. Okay. Now one, two, three, 4, 5, 6, Now the input shaft has completed 7 complete revolutions. As you see here, the flange has completed 1 complete revolution, meaning our calculations are correct for the first gear ratio. Okay. Now I repeat for the second gear ratio also now. Then for the second gear ratio, we know that second gear ratio is 4.3, almost 4 and a quarter turns of input shaft. Okay, let us see. Now engage the second gear. Now the marks are at the top. I rotate the input shaft, applying second gear. 1, 2, 3. Now I completed 4 revolutions. The flange almost came to top. Now a further quarter turn will bring the mark to the perfect top. So the second gear ratio is 4.3 is also met. Likewise, I engage the fifth gear now, the direct drive that couples. So now the marks are at the top. I made 1 complete revolution at both input and at the output shaft as well. So the fifth gear ratio also met. Now I going to engage the reverse gear. Now I engage the reverse gear. Reverse gear, we have to observe 2 things. One is the flange has to rotate in the opposite direction, as well as it has to maintain the 6.6, almost 6.5 revolutions of input shaft turn has to maintain. Now I start. Now I turn the shaft in this direction, but the flange is going this way. So the reverse gear is engaged. Now 1, 2, 3, 4, 5. Now I made almost 6 turns. Now it is going to come for extra half turn. The flanges came to topmost position, that is 6.6 turn revolutions of the input shaft made the output shaft rotating in the opposite direction. So the gear ratio calculations are met. Now I going to cover the top portion of the gearbox. As we discussed earlier, there are 2 kind of mechanism, locking mechanism are there at the selector rods. One is interlocking mechanism, the other one is detent. This thing is the ball and spring arrangement makes sure the given selector rod will not come out from its engaged or neutral condition. For that we need to put a ball and a spring. This spring tension will take care the unnecessary movement of the particular gear selector rod. Likewise, for every single rod there will be a 1 ball and a spring will be there. This has got, previous version has got 4 selector rods, that is why they are given 4 selector grooves and balls. In this particular model we have only 3 selector rods, and this is interlocking pin. It will be coming here. It will, whenever you engage one gear rod, it will prevent the other gear rod getting engaged to the other gears. So it is interlocking mechanism pins. Now I am going to assemble the selector rod with selecting forks. So these 3 forks respectively should sit on the respective collars such that the gears will engage smoothly. Okay. Now I engage the 5th gear. Now it is a 5th gear condition. You can see now that it is rotating 1:1 ratio. If I now move this way, the 4th will be get engaged. You can see the 4th gear is engaged. It is neutral condition. Likewise, all the gear rods can be activated for the particular gears to be engaged. This top cover. In this, I am not going to assemble the clutch cover housing and the clutch withdrawal levers. With this, I conclude this session. In this session, we have discussed how to dismantle the gearbox that are used in Ashok Leyland trucks, 16-ton trucks, and we discussed how to calculate the gear ratios, and the number of teeth present in each and every gear are given in the table itself. and we have seen how the architecture and how the construction of the gearbox. So, thank you for the session. If you have any doubt, please come to the forum and we shall discuss in the forum. Thank you.